Okay, cool. Great to see you all. Thanks for coming out to listen to our talk on SkyRL TX. TX has been our initiative to build an open implementation of the Tinker API, which Thinking Machines released a few weeks ago. We've only been working on this for about a month, but we think there's a lot of exciting things to talk about in our design and progress so far. And then we'll also talk about some of the next steps and what we see going forward. To start, I wanted to say, when we were preparing this talk, and maybe also across the project in general, we had a few target audiences in mind. So perhaps you're a researcher or open source developer who likes Tinker, but maybe you want to, change some aspect of it or use it in some different way from the existing hosted service. So perhaps you want to implement your own model or do full parameter fine-tuning instead of LoRA. Or maybe you're an engineer and you want to stand up your own Tinker API-compatible service that actually runs the Tinker service on your own hardware in your own environment. Or maybe you're just curious and you want to learn a little more. And actually, we think this is a great time in terms of the state of the project to hear this talk and maybe even poke into the code, because it's still, we think, still quite simple and easy to read. And so it's a lot of fun seeing how one might implement a Tinker-like service where you have MOE models, you're training LoRa adapters on behalf of many clients. We'll get into all those details more later, but I just wanted to say the project is at an early stage where it's still quite hackable and easy to dig in and understand the code. And so I wanted to start by giving a brief overview of the Tinker API. I know the Thinking Machines folks gave a keynote earlier today, so there may be some duplicated content here. But if you're interested in for more detail, by the way, I definitely recommend you check out the docs for Tinker. They're really quite nice, and when I was reading through, there are many interesting tidbits that I learned from reading them. But I want to mention a few things about the API. The first is that really a core part of the design and benefit of the Tinker API is it allows the user to write their simple, high-level training loop that's going to be executed on their own local CPU-only machine. And the actual heavyweight work of training and sampling, it occurs on GPUs elsewhere. Essentially lifting the level of abstraction that a user has to interact with in order to implement and execute some training run. The API itself really boils down to 4 core methods that unify both training and sampling under one interface. So you have your forward and backward passes, you can step the optimizer, you can sample from the model to get generations, and you can save and load your training state. And the idea is that though simple, these are sufficient in composition to implement the various training methodologies that you may be interested in, like if you're doing some SFT or DPO or RL, or even your own custom differentiable objectives, you can implement your own loss. And finally, the Tinker API itself does not place any constraint on using LoRa adapters rather than full parameter fine-tuning, but the service as it was originally introduced is multi-LoRa, meaning there's LoRa adapters on a per client basis, and you have the opportunity to multiplex GPU resources across many individual users' training runs by training on multiple LoRa adapters sharing the same base model parameters. And I wanted to stop and take a moment of, I've told you some things about what the API is, but I want to tell you why this is something that we think is interesting and exciting and worth building an implementation of an open source. And the first is, as I said on the first bullet point, is that it really lets AI researchers ignore the infrastructure. So this simple training loop that folks implement is generally much higher level. You focus on the data and the flow of your data across these various operations like forward-backward passes and sampling, and you can largely ignore all of the complexities that's happening under the hood to actually execute this efficiently, to scale this, how it may look different for different base model types. And so I think it just really lowers the friction for AI researchers to iterate quickly and do research quickly on the actual aspects of training that they care about. And we also think this is the right level of abstraction, where it's still, as you see, an extremely simple interface, but expressive enough to capture the training methodologies that we're all interested in. And we think because of these reasons, there's an exciting opportunity for standardization, somewhat akin to the OpenAI API for inference, We think it would be awesome if there were more projects and research and frameworks that are built targeting the Tinker API, such that it becomes a lot easier to take advantage of the awesome community that is open source. Because right now, in many of the open source training frameworks, if you write a new training loop that you think does something cool and interesting, it's really quite hard to take that and import it into another training loop, or into another training framework, because of the fact that many of the components in that loop are going to be specific to the way that the actual GPU workers are operating under the hood. So we think there's also an opportunity to standardize and develop more libraries and utilities all targeting the Tinker API that can be shared and built upon more widely. And so when Tinker was released a few weeks ago and we got excited about it and started wanting to build an open implementation, we saw a couple of different ways that we could approach this. The first being we could pick up an existing training engine off the shelf, pick up an existing inference engine off the shelf, and implement whatever compatibility layer is necessary to implement the actual Tinker API with these stacks. And some benefits of doing this is these are mature and rapidly maturing and improving stacks. And so we can use these existing high-performance, high-quality implementations that already come out of the box with their optimal sharding or parallelism options. The second approach, which we opted for, at least to start, is implementing a common engine for training and inference. And what I mean by this is that as opposed to picking up two independent mature stacks and trying to combine them, instead we wanted to explore what it would look like to really dig into this interface that unifies both training and sampling and see what it would look like to implement one common engine that does both sampling and training, where at a reductive description could be imagining an inference engine that also happens to do backward passes. And so some of the early benefits of doing this is it is just simpler, so we can share a lot of aspects of the implementation between the inference logic and the training logic, like the model definitions or the multi-LoRa implementation, or there's guaranteed commonalities between how we're doing checkpointing and managing checkpoint formats, and doing sharding between the sampling and the training stacks. And because of the simplicity, it makes it a lot easier to share GPUs between training and sampling. It makes it easier to align the numerics between the two. It makes it easier to synchronize weights after they're updated. And so we've had a lot of fun trying to explore what it would look like to build a post-training framework if from day one you consider that inference and running generations was a fundamental part of the post-training stack, as we see become increasingly true as reinforcement learning has become popular. Despite the fact that we chose the second option, I wanted to be clear, we don't think there's anything wrong with the first, and it's actually not unlikely that we end up converging to something like the first, especially given the, some of the fundamental differences in the workloads between training and inference. There's good reason that there are separate mature stacks for these two things, but maybe as a function of me being a PhD student and Philipp being a fundamentally very curious person, we just wanted to explore what a unified engine would look like. So that takes me to jumping into the architecture of SkyRL TX currently. So the way I want to walk through this is by essentially walking through the lifecycle of a given request. So to start, a user or a client is on their laptop, and they're going to send some request to the Tinker API. And as an example, this might be just a script that exists in the Tinker Cookbook, which is the open repo that Thinking Machine published with some examples of training loops that targets the Tinker API. In TX, we stand up a REST API server that exposes the Tinker API methods and receives these requests and then persists them in a database that tracks the pending job queue across multiple clients, as well as any metadata attached to each request, like which client and which LoRa adapter does it correspond to. This request will then move to the execution portion of the framework, where first the engine, which is running on CPU, is batching the requests and scheduling them for execution. So since we have a shared base model with the per client LoRa adapters, we can batch forward and backward passes on behalf of many clients to run shared forward and backward pass across all of them. So this is the aspect that takes advantage of multiplexing GPU resources across many clients. So the engine is going to make batch scheduling decisions and then pass this off to workers. And so these are what are actually running on your accelerators. This is what's running on GPUs. So the workers are actually executing the requests. They're running forward-backward passes. They're updating per tenant optimizer states. They'll also checkpoint. And so we can save model checkpoints either to local storage or to the cloud in the persistence layer. And also wanted to mention the current implementation is JAX-based with PyTorch planned for the near future. So I think still relatively simple and intuitive, and so I want to double click on the point that now's a great time to jump in and contribute if you're excited about this, because it's still quite simple and easy to dig into the code. Before handing off to Philipp, I wanted to conclude with some features in our progress along the way. So as I mentioned, we started this roughly almost exactly a month ago, and we've been trying to regularly keep the community updated on our progress so far. And so we started with just supporting the Qwen3 model with basic multi-LoRa support. And as we've gone over the weeks, we now support LoRa in many of the layers throughout the model. So including, we support Qwen3 MOE models, the LoRa layers in attention, JIT compilation for faster training, gradient accumulation, so we can reduce the memory pressure. We then, last week, added the support for the sampling endpoint, and supported full checkpointing of training state, RL loss. At this point, I'm just naming many features, but where that's taken us is to our ODA1 release, which came out yesterday. An exciting part of this is that we can now take the scripts that are in the Tinker cookbook, so the canonical example scripts for training on the Tinker API, and run them out of the box, both the SFT and the reinforcement learning training loop, which is the first test of combining both sampling and training in the loop. And so much of this work was also done by a lot of great external contributors, and so we would be super welcoming for more to come help out. Now I'll hand off to Philipp to dig into some more implementation details of what we've done so far.
So first, I want to talk a little bit about the performance optimizations we have been working on. Obviously, performance is really crucial here, given that GPUs are in such scarce demand, scarce availability. One very important optimization here is making sure that everything can be JIT compiled. So it gets rid of all the Python overhead. It uses things like CUDA graphs, for example, for the decoding, and also it can optimize some of the kernels on the fly and do some fusions and stuff like that. For that, it was really important to make sure that the tensors are padded, because otherwise for each separate shape, you're going to rerun the JIT, and you want to avoid that. So what we do there is actually we take the sequence length, and then we round that to 2 digits in binary representation, and then round it up. And then we use that as a padded dimension, and then make sure that both there's only few of these shapes, and also there's not too much overhead in terms of additional tokens that we have to process. We also implemented KV cache for the decoding, and at the moment our implementation is actually fairly simple. It just uses a contiguous cache. Later we are planning to work on page attention also for the inference. And then we did a bunch of memory optimizations, like micro batches, both for sampling and training, and then also gradient checkpointing for the training. In terms of the future, we are planning to do a bunch more optimizations, like page attention, but also prefix caching so that KV caches can be reused. Possibly also even in the future, if you do context parallelism for training, you can even reuse the KV cache to do the parallelism, and then also do more specialized and more fused kernels in the future. I wanted to take a little bit of time to go into the more internals, and there's actually some very interesting stuff here that some of you probably already know that, but I'm sure it's also new for some of you. The first one is the concept of a ragged matrix multiplication. Some people also call it a grouped matrix multiplication. And that's really a very central primitive that underlies both the multi-LoRa as well as the MOE stuff. So how this works is you have a long vector of tokens or states associated with these tokens. So here I took an example of expert routing, where each of the tokens goes to a different expert. And then what you do first is you sort it, and then you get this representation here. That's why it's called ragged, because each of them might be slightly different length. And now you want to apply your experts to the vectors. So you invoke this ragged dot kernel. And that will then apply the expert 1 to all of the vectors associated to expert 1, apply the expert 2 to all the expert 2 tokens, etc. And then you get the outputs. For LoRa, it would be the same, but instead of experts there, it would be different LoRa adapters. And then you take the output and you unsort it. So you just undo the sorting, and then you get the output states. And that's an efficient kernel that in PyTorch it's called grouped MM. In Jax it's called ragged dot. And so this we can now use to implement the multi-LoRa. And this code is actually, it's extremely simple, but this is actually the actual code. So like, that's really how simple it can be. So we have this LoRa mix in, which allows you to add basically LoRa to like any layer, which has like the different scale factors for the different adapters, the ranks for the different adapters, and then the LoRa A and LoRa B matrices. These are the two low rank matrices for the LoRa. And then it has this apply LoRa function, which takes the normal inputs plus these adapter indices that tell you which tokens go to which adapter. And then it just computes the sorted tokens, the different sizes of the groups. So these are like these group sizes, like the number of vectors in each group. And then the unsorted indices. And then it computes the two ragged dots, one for the LoRa A and one for the LoRa B, and then unsorts the output and adds it to the base. So that's how simple a multi-LoRa implementation can be. And then in order to put it into the model, for each of the layers of the model, we just inherit from the class. So in this case, it's implemented for the linear class. We inherit from the linear layer and also from the LoRa mixin. And then we just implement it by first computing the base layer and then applying the LoRa. And then, as you see, here's another example for the MLP. Like that's just a bunch of these LoRa linear layers. So you just replace linear by LoRa linear, and that's it. And then here's a picture of how this actually looks in terms of the model. There's the base model, and it's shared by all the LoRa adapters. And then I don't have the code for that, but it's similarly simple. You just have different optimizers for the different LoRa adapters, and then you can do the training with the multi-LoRa. That was one of the innovations of the Tinker API. People have been doing multi-LoRa for serving systems for a pretty long time, but like also doing it for the training is a very good idea, and then you can do multi-tenancy on the GPUs. Because, as I said, like the multi-LoRa is not only used for, the ragged dot is not only used for multi-LoRa, but also for MOEs. It's also very easy to implement the multi-LoRa MOE implementation. Here we just set up the routing to be in the whole product space of adapters and experts. So like for MOEs, we route to the different experts. For LoRa, we route to the different experts. If you do for the different adapters. If you do multi-LoRa MOE, we just route to the joint adapter expert space. And so you take the tokens or states, and you route them like is shown here. And the code is actually very simple. If you look at the repo, there's a PR implementing it in like very few lines of code. Cool. So now at the end, I wanted to talk a little bit about the sharding. So that's something we will work on actually a lot more. We already have tensor parallel sharding at the moment. And like that was one of the reasons why we chose Jax for the first version, because it makes the sharding actually very easy. Like you don't need to implement any communication or anything like that. You can just annotate the model graph with the sharding annotations. So here you see again this MLP. It's actually the same code as before, but now I show a little bit more detail about the parameters. And when you put the initialization for the kernel, you just say, instead of just saying the initialization, you wrap it in a with partitioning call. And then here you see the checks.p, and it tells you that the first part should be replicated, and the second part should be, the second dimension, like the intermediate dimension, should be sharded across the TP dimension. That was all that was needed to implement the sharding. So then the next sharding we will probably implement is FSTP, and that's actually, it fits into the framework as well. You just now need to replace the none with like FSTP, and you add one dimension to the mesh, and then that gives you FSTP sharding. And then in the future, we will also implement shardings that only apply to transformers, like the pipeline parallel, context parallel, and expert parallel sharding. Here's a picture of the pipeline parallel. Cool. So I wanted to also say a few words about the development. Our philosophy here is make everything as simple as possible. The code should really reflect the idea. And like, I think you see that with the sharding, right? Like, you don't want to have a lot of code around the sharding. You just annotate like what should be sharded, and like that's it. And also, we are trying to not cut corners and make it so that the code can be as powerful as people want it to be, because this is an open source project. So we anticipate that people want to modify it for their own users and stuff like that. So like everything should be well implemented and extensible. And LLMs actually help a lot with that. They make it very easy. We use them a lot. They make it very easy to try out different ideas and see like, oh, if I would implement this like slightly differently, how would the code actually look like? And then you can select the best implementation out of those. And we use a lot of the different models, and we also do a lot of reviews and like work on the code until it's really like very nice. So I think this is also a very good way to learn about like how can a Tinker-like thing be implemented by just reading the code. It's very simple. And then we would also like to welcome contributions. There's a lot of interesting work to do, I think. One possible thing for the future is to implement just an OpenAI or Anthropic compatible API and make it possible for people to infuse the rewards as part of the API, like either with like some headers or by extending the API. And then you can do continual learning and like use this as an inference engine that can also do backward passes and like learning. We would also welcome more model implementations. Currently, we only have Qwen 3 because we want to focus on doing one thing well, but like we would also really welcome like Llama, DeepSeek, also multimodal models. These can also use some of the same ideas with the ragged dot and this kind of primitive. And then also, if people are interested, that would require more coordination, but we are very happy to work with you to implement more sharding mechanisms like the FSTP, PP, context parallelism, expert parallelism, and so on. And even though the project is relatively young, we actually already have a bunch of very good contributions. Some of the contributors actually in the talks. So Atom, Colin, Guido, Kranti, Lucas, Murali, Pranav, and Rohan. So thank you a lot for your contributions. Cool, yeah, that's all. Yeah, if you'd love to chat with you, we have a Slack channel, and then there's also the code that's up on GitHub, and yeah. That's it. Are there any questions? Oh, yeah, please.
Might be a basic question, but we've seen a lot of AI frameworks being developed. We've seen a lot of AI frameworks being developed for running on bare metal or virtual machines and then being ported to Kubernetes. So I know the project is in its infancy right now, but I'm curious if you are thinking about, hey, are we going to support Kubernetes as a first-class deployment platform, or you're too far away from that decision right now?
So, I mean, we will make it flexible. Like, given, I mean, like Anyscale and, I mean, I want to create as of Ray. So, like, we will make it work very well on Ray. Obviously, that's one priority. But, like, not, like, there's people who have, for various reasons, run it on different things. So, like, that will be a little bit more work. But, like, we will make sure that these things are supported. Yeah.
Thank you.
Mm-hmm.
A quick question. So you mentioned about the first version only support JAX, right? I'm trying to understand what's the motivation for that. Is it because of like JIT, GSPMD, or like XLA, you can support different accelerators, or some other reasons? Yeah.
So it's a variety of things. Like one is definitely being able to move very quickly and like get a lot of stuff for free, like the sharding. You don't have to deal with like CUDA graphs and that sort of stuff. So it makes it a very you can have a very minimal implementation that is still very high performance. That's the initial, one of our initial motivations. But we already have a plan to, so we will probably relatively soon shift the model definitions to PyTorch. There's a way to run PyTorch, basically run PyTorch code and then let it be executed as checks. That will be the, because we realized that a lot of people like PyTorch. So for people to be able to contribute much easier, we will port the model definitions. And then we will also like slowly start working on a backend that can run with like pure PyTorch stuff, and we welcome contributions for that. But there's a decent amount more like work you have to do for that in terms of sharding and stuff like that. And in order to be able to experiment quickly and make this like unified training and inference engine a reality, and like try out the different design decisions there, like JAX is a really great way. Plus, you also get running on GPUs and like other hardware platforms for free. So yeah, that's a nice plus.
Yeah, thank you. Thank you very much for the very interesting talk. Do you have any plans to introduce speculative decoding or doing something with that for your framework? For example, you could retrain the draft model using your framework. Is that something you are considering?
I think it's a neat use case. I mean, like, it depends. I mean, in terms of our priorities right now, there's a bunch of lower-hanging fruit, I think, on making the inference faster, including like page attention and also like the kernels. But like, we very much will welcome contributions for sure. And like, once it makes sense, we will even work on it ourselves. So like, and I think I haven't even thought about this, but like having the draft model being retrained as you go, that's a very neat use case. So it makes a lot of sense. Like if you're interested in contributing, like, yeah, you'd love.
I also wanted to add, this also seems like a great use case for the Tinker API itself, which is that now like in your control loop where you're maybe operating between both the draft model and the policy model that you're trying to train, in theory, again, we're thinking of this now for the first time, in theory, like this, you can write this control loop at quite a high level that just details your logic between the two without caring at all about the fact that presumably behind the scenes we have like a smaller base model that has one LoRa adapter and maybe a larger base model that has a different LoRa adapter, and clearly like the outputs of some of the draft model are being sent somehow to the larger model. So anyways, I mean it seems like a pretty fun use case to test the implementation of this multi-LoRa Tinker API.
In general, I would say like it's very interesting to think about like the unified training and inference stuff, and like what are sort of the things that this allows you to do. And like I think the reason that people currently build separate stacks for that is probably mainly because of different people working on it. And like, but if you think about it like end to end, there's actually a decent amount of like interesting common things that you can do in that setting. So yeah.
Hi, thanks for the talk. And you guys displayed two backend options in the beginning, like either figuring out the inference and training or like re-implementing everything like from the get-go. I'm wondering, right now you have on the roadmap a lot of options that could be deviated to the first option. So what was very problematic with going with the first roadmap itself? Like page attention, sharding, all of that stuff is kind of figured out in either of the two boxes you displayed in the beginning.
And we will support that. Like, there's actually already PR that we will merge, where like you can just configure VLM as a backend, and then people can just like run. There are people who have like really figured out a very efficient way to run things with VLM, right? Like, I mean, maybe they do like pre-fill, decode, disaggregation, or they have like customized kernels and stuff like that. So like reusing a lot of that stuff, making it possible for people to reuse, I think that's very valuable. The advantages for like doing everything in one engine is like a lot of, it makes it very easy to get the numerics right and like make that consistent between the two. If you work on like the determinism, you can do the work once and like get it for both. It makes it possible to use the same GPU fleet for like both inference and training. So like there's a decent amount of like fundamental reasons why it's a good idea to do them in one framework. But like, I mean, we're not going to limit to that. So like, and we will also support it if people want to bring their own inference engine.
And there's also a dimension of it being exploratory. Like as Philipp was mentioning, we want to see if there are some synergies that exist between the way you implement the training and inference stacks. If you assumed as like a first-class citizen that they're both operating behind the same API, because up to this point, I think these are two largely independently evolving stacks, your training and your inference stacks. So we'll also see if we find some interesting ways that we would rethink the design of a post-training stack that unifies the two of them.
Hi, I guess it's maybe a tangential question. I was just curious how you found the performance of JAX or like the XLA on GPUs to be like, sorry. Yeah, I'm assuming you're using GPUs for all your work.
We use GPUs a decent amount. I think we're not to the point yet where we try to squeeze out every little piece of performance. At that point, that's one reason why like a PyTorch backend might make sense in the future, right? To use like better optimized kernels for GPUs. So far, we haven't run into like bottlenecks that are like big and glaring. But like I think once we are at the point where we really try to squeeze out the last like 10% of performance, then I think it's a lot. Yeah, there might be a lot more stuff. But on the other hand, I mean, you can also integrate all the existing kernels. So like, yeah, it's a bit of an open question, I think.
Thank you.
But JAX is also getting more popular. I mean, SGLang now has a JAX backend, like VLM has a JAX backend. So like, yeah, and I think a decent amount of the frontier labs are actually using it for like pre-training and stuff like that.
Yeah, thank you for the talk. Very excited about the project. So I wanted to ask, what's the current state of support for multi-node? Like having a model that's distributed across multiple nodes, not like multiple GPUs, but actually multiple nodes.
Yeah, that is actually the very next thing we're going to tackle. So like, as you see from the feature list, like so far, there's a lot of low-hanging stuff that we need to put out. But like for the FSCP stuff, actually, we will implement the multi-node support. So tensor parallelism work, like, makes sense on one node, but like for the other parallelism strategies, this will be basically the next feature that we will work on.
Hi, so the option one that you had, right, like using VLLM or Torch Titan and stuff, right? It's not like fair comparison, right? In the sense, like if you're trying to unify it, if you pick one for each, then you're just building a wrapper, right? And I'm not sure if that really helps with what you're trying to build out, right? So I guess, is it fair to say that this is not really a fair comparison? Like that option one is not even a fair route to go.
Oh, I see. I mean, I think it's actually like existing open reinforcement learning stacks, for example, I think largely fall under option one, where they'll pick a training backend, maybe Megatron or Torch Titan, they'll pick an inference engine, and then a lot of the new code in the open RL stack is like the glue code to get things to work between them. So to synchronize updated policy model parameters from the training stack to the inference stack, to send like completed rollouts and rewards from the inference to the training stack to update the model. So I think in many of the RL stacks, that is somewhat the status quo. I think one aspect, though, is that it is not the case that these frameworks that we have pulled up here, like they definitely don't implement their like under the Tinker API. So there would anyways be like some, I don't know, compatibility layer required to convert the Tinker forward-backward pass into whatever that looks like in Torch Titan. Does that address the point you made?
I guess I'm saying like if you are set out to build a unified engine, right, for inference and training, right, then I guess like the approach 2 is the only thing that makes sense, right? Like I guess well, I understand like for right now in the state of affairs is that like, hey, you have to do it quickly, so you just pick whatever is out there in open source and whatever is the best for training versus inference. But like going forward, yeah, I guess.
I do think it's a valid way to build this. Like, if you have enough GPUs that you can afford to just run separate stuff, right? Then this option is like a good way. And like, I expect people will use our stuff even in that mode, because like I think at the moment there's no good like multi-LoRa training framework, so you can just use like the backend we have been building as a multi-LoRa training framework. But then the inference engines, most of them support multi-LoRa like out of the box. So like if there are some advanced features that we don't currently have in our inference code, like it is a very valid way to, I think, just use an open source like an existing inference engine and then use our backend just for the training. So I think that the design space is pretty big.
Okay, thank you.
So the question is, many inferencing workloads have very different characteristics from training workloads. That is true, but also not true. Like if you look at the sharding, actually there's a decent amount of the like work that is going on in the inference is actually sort of converging towards the training sharding in some senses, like doing like context parallel things, like obviously the tensor parallel is like the same thing, and you can also use the FSTP sharding. Like there's a decent amount of like commonalities, I would say. And in terms of the workloads, like if you do RL, for example, then I mean a lot of the stuff that you're doing on the inference will sort of be mirrored by what you're doing on the training, right? Like the kind of requests that you will work on during the inference, they will be the same as the requests that you will work on during the training. So there's a decent amount of commonalities. So like it's, yeah.
Just a follow-up. For example, enterprise AI, right, edge AI, those have latency requirements that cloud AI cannot meet at inference AI.
So the way we are building this is actually more like we built this like an inference engine that also supports the like backward pass. And there's no reason a priori why you can't get the same latency requirements that a good inference engine can get. So like,
Thanks for the great talk. I got two quick questions. One is, how does the SkyRL TX fit into current existing SkyRL stack? And secondly is, this might be premature to ask, but from your perspective, what would be a good outcome from this project in 6 months?
Nice. I can start with the first. Yeah, so currently SkyRL TX, it's in the SkyRL repo, but it is itself a standalone project, a standalone sub-project. I still would be very excited for this to, whatever we end up building here, to serve as a backend that can be used in the SkyRL like core training loop. I also think anyways, in the like core SkyRL framework, it would be awesome to support Tinker compatible training loops anyways. And so I'm hoping that there's a lot of like transferability between the code that we're writing here and what can gradually be ported into the SkyRL code core stack. Your second question was, what is a vision looking 6 months forward? Everyone in the world using SkyRL TX. No. Yeah, I think a couple things. One, I mean, of course, we mentioned in the near future, there's like a lot of low-hanging both fruit for both performance and just expanding support for new features like the parallelism and sharding strategies. I think it would be awesome if we, as we've discussed here, have found more synergies between training and inference, such that we have something new and interesting to say about the way we feel like you should build this unified post-training stack. I think what would also be awesome is if we could get people to use this as a service. So like one starter idea is, I am in a PhD lab of many students who don't want to care about or think about the infrastructure. It'd be awesome to stand up our own internal service in the lab and get some experience actually operating this thing and having my fellow students train their LoRa adapters on it. I don't know, do you have other visions?
And I mean, the Tinker API, I think it's like very well done. And like, there's a future, I think, where like a lot of more people are interested in that kind of API. And then having a good like open source backend for it is very valuable, right? Like some companies might want to like do some modifications of their own, or like, and they might run it on like some data that they don't want to like share with like some hosted service or things like that. And so like, in the same way that VLM is like a very valuable thing for the OpenAI API, right? And like having an open source implementation of that is very valuable. Like in the same way, I think here it's very valuable to have a good open source implementation. So that's sort of what we are thinking about. And hopefully there's a lot more contributors, and like it has like all the features people want, need, and like the performance requirements and stuff like that.
Okay, I think that's time. Thank you, everyone. Appreciate it.